Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, today we are going to start the new topic, that is stresses due to bending. So, already you know what is bending and how it affects the slender member, right. Already we have seen that bending moment and shear force, all those things, how you can calculate over the whole span of the slender member. Now, we are in this particular chapter, we are going to discuss the stresses developed due to bending. Now, first we will be talking about geometry and deformation of a symmetrical beam subjected to pure bending. Okay. Now, in this chapter, if you look at, so we will be talking about in the slide you can see that we will be discussing moment curvature relationship for pure bending of beams with symmetric cross section, bending stress and shear stress. Okay. So, first we will be talking about, we will be concentrating on the bending stress determination, and then we will be talking later on, we will be talking about shear stress determination. Now, first what we are talking about, we are going to find out the geometry of deformation. Okay. So, due to bending, okay, when the slender member is the action of bending moment, okay, when it bends, right. So, at that time what kind of say deformation and how the geometry of the deformation is taken place. Okay. So, of a symmetrical beam subjected to pure bending. Now, what is this word pure bending? So, pure bending is nothing but a beam which transmits a constant bending moment is said to be in pure bending. Okay. That means there is no shear force. So, it might happen, right. So, if you consider a a slender member, a beam, right, which is subjected to the bending moment in such a way that you have the constant bending moment throughout the span without any shear force. Okay. The shear force is completely 0. That kind of situation might happen in the beam, and under that situation we are going to find out, or we are going to analyze the system for stresses and deformation. Okay. So, now since our originally straight, so originally straight beam, so you know that originally straight beam, so this is your say beam. So, originally straight beam, okay, and after deformation or after bending it will take the shape like that. Okay. So, originally straight beam is now becoming the curved one, isn't it? Now, after deformation it takes the curved shape. Now, therefore, it is useful preliminary step to introduce the concept of curvature, because that curvature will try to define the deformed shape of the beam. Okay. So, let us talk about the curvature first. So, what do you mean by curvature of a curve? So, as you know from your mathematics that the curvature of a plane curve is defined as the rate of change of the slope angle of the curve with respect to distance along the curve. Okay. So, this is the definition, proper definition of the curvature of a curve. The curvature of a plane curve is defined as the rate of change of the slope angle of the curve with respect to the distance along the curve. Okay? Very simple definition. Now, if you look at this plane curve, say A, B, C, D is a plane curve. Okay? So, A, B, C, D. So, that means this is one plane curve, okay, and whose curvature is actually in xy plane. Okay, this is the plane curve and the curvature is in the xy plane, and this B at this is the normal to the curve at point B and normal to the curve at point C, they are intersecting at say point O prime. So, understood. So, normal at point B on the curve and normal at point C on the curve, they are intersecting at say point O prime. Okay. Now, this the change in the slope angle, the change in the slope angle between B and C, between this point and this point is nothing but say this is your delta phi. That is the change in the slope angle between B and C, because at each and every point, I mean this curve is showing you that at each and every point your slope is changing. So, the change in slope between B and C is a delta phi. So, when delta phi is very small, right, at that time the arc delta S, okay, can be written as O prime B, that is the radius of the curvature multiplied by delta phi. Can I write that? So, delta S is equal to O prime B into delta phi, as delta phi is if delta phi is small, right. So, that is the condition. So, if delta phi is small, the arc delta S is approximately, okay, is equal to O prime B into delta phi. So, what we can write now? We can write as delta S tends to 0, okay, the curvature at point B is defined as your d phi ds, because that is the definition. That means is defined as the rate of change of the slope angle of the curve with respect to the distance along the curve. So, d phi ds is your curvature, which can be written as limit del s tends to 0 delta phi delta s, okay, agreed. So, that can be further written as delta phi is very small. So, we can write down this thing as delta phi O prime B into delta phi. So, limit delta S tends to 0, okay, we can write that. So, this can be further written as limit delta S tends to 0, this is O prime P, and this can be written as 1 by rho, where rho is equal to O prime B is the radius of curvature at point B. Okay. So, the definition of curvature is nothing but 1 by rho. So, 1 by rho means the radius of curvature, right. So, that we have got here. So, that this expression will be frequently used to define the stress due to bending. That is why we are doing this exercise. So, that some recapitulation also will happen, and at the same time you will appreciate that this 1 by rho term will be frequently used, because the plane beam is now taking. So, this was the beam before bending, and after bending it is taking the shape of some curve. So, therefore, radius of curvature is very say important parameter, okay, to define the deformation due to bending. Okay. So, now it can be shown, it can be proved also, it can be shown due to by following the symmetry argument, it can be shown that in pure bending, okay, in a plane of symmetry, the plane cross sections, okay, remain plane even after deformation. Okay. So, you are starting with some plane cross section, and in the plane of symmetry basically that plane cross section will be remaining plane even after deformation. So, that can be shown. So, well, so now basically if you look at the deformed shape of the beam due to pure bending, that means I have the beam like that, okay, and say this is my deformed beam, okay, which is taking the circular arc, okay, fine, and this is under the action of bending moment MB, because this is pure bending. So, only bending moment, okay, constant. Now, if you look at this top fiber of the beam, okay, it is getting shortened, is not it, this concave, because as you know this is I am showing the positive bending moment. So, the top fiber will be experiencing the compression that will be coming later on, okay, because it is getting shortened. So, when it will get shortened, if you compress it, right. So, this fiber is basically getting shortened, right, whereas the bottom fiber of the beam is getting elongated. So, from this at least we can say something from our intuition that the top fiber should experience some compressive stress, and the bottom fiber is is experiencing or should experience some tensile stress. So, whether that thing is coming from the analysis or not, that we are going to say. Okay. So, now if you say the bottom fiber is getting elongated and the top fiber is getting shortened, then there must be one line in the plane of symmetry, okay, which has not changed in the length, and that line is known as the neutral axis. Understood? That means, if you move from bottom fiber to top fiber, okay, there must be some line in between which will not experience any kind of deformation, no elongation, no contraction, because because you are traveling from the elongation to the shortening, right, or the contraction. So, there must be one line in between where you should not have any kind of deformation, and that line is known as neutral axis. So, this is very important in this discussion. Okay. So, this is your neutral axis. Now, let us try to define the neutral axis, and now the location of the neutral axis we do not know, frankly speaking, at this moment. We will try to find out the location of the neutral axis later on, but at this moment from the discussion it is coming out that there must be one line where you will not get any kind of deformation, and that line is neutral axis. It is completely neutral in terms of the deformation. So, if you look at this figure actually, so this is your neutral axis, and this neutral axis is basically, so this is your bottom fiber, Okay, this is your bottom fiber of the beam, this is your top fiber of the beam, and this x axis we are saying the neutral axis, but we are not talking about the location, because location we do not know. We are just saying that x axis is, or we are forcefully we are making the x axis as the neutral axis, that we are doing. Okay, and this is your plane of symmetry, fine, this is your plane of symmetry. Okay. So, now we are considering two fibers, one is your ij, okay, some distance above the neutral axis, and one fiber say mn which is at the neutral axis. We are considering two fibers, right. So, I mean before deformation basically ij is nothing but mn, because there is no deformation. So, all the fibers are equal. So, ij is equal to mn because no deformation has happened. Now, after deformation, if you see the deformed configuration, so this is your deformed configuration. Okay. So, now here your earlier it was ij equal to mn, right. Now, even we can say mn is nothing but equal to m1 n1 even after deformation, because mn fiber lies in the neutral axis. Okay. And mn fiber, because it is lying on the neutral axis, so mn fiber should not experience any kind of deformation, like with no elongation, no contraction. So, even after deformation you are getting m1 n1, right. So, that must be equal to ij and must be equal to mn, but at the same time your ij fiber will be experiencing some deformation, and because neutral axis is not experiencing the deformation. So, anything above the neutral axis will be experiencing the contraction, and below the neutral axis it will be experiencing the elongation, right, because you are crossing from elongation or you are travelling from elongation to the contraction zone. So, therefore, I1 J1, okay, this fiber is getting compressed, or the contraction or the shortening is happening in this fiber, right. So, if I define the radius of the, this is a circular curve, right. So, this arc is circular, okay, because it is a pure bending case. So, it will take the circular shape because it is everything is symmetry. Okay. So, the radius of the curvature is say rho, fine, and this fiber I1 ij or I1 J1 is lying at some rho minus y distance, okay, from the center. So, this is the center of the arc, fine. So, this distance is say y, that is given here, okay, fine. So, what I can write epsilon x equal to, and this is happening, this contraction in ij fiber is happening in x direction. So, epsilon x can be written as I1 J1 minus ij, that is the difference in length, okay, divided by the original length, okay, that is happening in the ij fiber. Okay. So, that can be written as I1 J1 fine, okay, minus M1 N1, because ij is equal to M1 N1 by M1 N1. I can write that. So, now if you look at the figure, M1 N1 is nothing but rho into delta phi. So, rho is the radius of the curvature and delta phi is the angle made, okay, that is the angle made at the center. Okay. So, I can write that, and your I1 J1 in the similar argument we can write rho minus y, that is the radius of curvature for that fiber, okay, multiplied by delta phi. So, therefore, your epsilon x can be written as rho minus y delta phi minus rho into delta phi by rho into delta phi. So, this is nothing but your minus y by rho, which, so what is your y by 1 by rho? 1 by rho already we have seen, that is d phi ds. So, I can write d phi ds into y. So, this is very important relation, okay. Epsilon x is equal to minus y by rho, okay. Now, this, why this minus sign is coming into the picture? Because this indicates that there is a shortening above the neutral axis, as we are talking about, right. This minus sign is basically indicating that you are getting a shortening above the neutral axis. If you go below the neutral axis, you will be getting plus sign, that means elongation is happening. So, neutral axis is the point or the boundary between elongated fiber and the shortened fiber, okay. That is creating the boundary between these two, okay. Now, we can conclude from the symmetry argument, right. So, this is the elongation happening in the fibers. So, if I consider different fiber in the beam, so each fiber will be experiencing some elongation or contraction depending on its position with respect to the neutral axis, that is okay, that we have got now. But from the symmetry argument, because the beam will be bending symmetrically, right, the plane of symmetry is there and it should bend symmetrically, because you have the constant bending moment throughout the beam. So, the symmetry arguments will require the plane sections to remain plane, already we have discussed, already we have decided, right. It can be shown also, though I am not showing that thing, but any textbook you will see that plane section should remain plane by following the symmetry argument. The symmetry argument already we have seen in case of torsion, if you recall, right, that was the symmetry argument, and that is very strong argument, at least in mechanics, okay. So, by following the symmetry argument, I can simply write the shear stresses on that plane basically must be 0, otherwise you will not be satisfying your symmetry. By following symmetry argument, your gamma xy must be equal to gamma xz must be equal to 0, okay. So, what you have got? You have got on x plane normal strain, you have got, that is equal to minus y by rho. On x plane in y direction shear strain is 0, and on x plane in z direction, that is gamma xz is also 0 to satisfy the symmetry condition. So, now if you recall your stress strain relation, everything is within your elastic limit. If you recall your stress strain relation for linear, isotropic, elastic beam, okay. So, for this kind of beam, your epsilon x can be written as 1 by E sigma x minus nu into sigma y plus sigma z, okay, which is nothing but minus y by rho. Already we have got it, just now we have derived. Gamma xy is equal to tau xy by g is equal to 0. Therefore, your shear stress is also must be 0, because the shear strain is 0, okay. Similarly, gamma xz is equal to tau xz by g equal to 0. So, tau xz, that is the shear stress on xz plane, is also 0 to satisfy this 0 shear strain condition, okay. So, the shear stress components tau xy and tau xz, they must vanish in pure bending. That is the biggest say finding, okay, from this discussion. So, only thing is that you will be, but still I do not know about sigma x, sigma y and sigma z, okay. The norm, we can't say anything about the normal stress, we have to do little bit more say analysis to talk something about or to tell something about sigma x, sigma y and sigma z. But at this moment only we can conclude that the shear stress tau xy and tau xz must vanish in pure bending. Okay? That is coming from these two equations. But from this equation we can't say anything about sigma x, sigma y and sigma z. So, we have to do little bit more exercise to tell something about these stress components. Okay? So, I will stop here today. So, in the next lecture we will discuss more about these things, and from there we will try to find out these stress components. Okay? Because if you know the stress components, then basically you can find out, I mean if you know the strain or if you know the stress, basically you can find out the actual deformation pattern and the stress developed due to bending. Okay? So, I will stop here. Thank you.